Today we're happy to welcome one of our own, Raghunathan, who's the Survey Science Fellow for CAPS at NCSA. The fellow who sends us our CAPS seminar reminders, and here he is in the flesh. So he's actually been here since 2021, but it's been, of course, challenging to intersect with people during the pandemic. So he's still new to many of us, and so we're very eager to learn about his research. He attained his PhD in 2016 from the University of Chile, working on the search for inflationary B-mode signals. And I think probably the most fun fact is how many places Srini has been. So he then was a postdoc at the University of Melbourne, and then at UCLA. So he's really traveled the world, and he's going to be telling us today about demystifying the dark side of the universe using secondary CMB anisotropies. Thanks, Tony. And do we have good audio, everything? Zoom?
Everyone on Zoom okay?
Okay.
We did have it.
We're okay then. All right.
Okay.
Yeah, we got with this one. Are you?
All right. Okay. Yeah. Thanks everyone for coming. Yeah. So I'm going to talk about what can we learn about the universe using the CMB secondaries. And here I have some figures, mostly from my talk. But I think I'm gonna concentrate more on KZ today, which is currently my main interest. Okay, all right. So this is the outline of my talk. I'll give a very brief overview to concordant cosmology, and then introduce the CMB, cosmic microwave background. I'll tell a little bit about the primary anisotropies of the CMB, but then go into detail about the secondary anisotropies. And then I will discuss the kinematic SZ and the thermal SZ, and how we can constrain physics of reionization, how we can constrain cosmology using these signals. So most of these things are coming from over densities in your universe, and if I have time at the end, also briefly show a few things that I've been doing when we cross correlate CMB with underdense regions in the universe. Okay, so here is our universe in a nutshell. So we believe inflation happened. We're still looking for the evidence or the smoking gun of inflation, which is the primordial B modes. So inflation happened, and then followed by that was a hot Big Bang, and the universe was very, very hot and opaque for the first roughly 400,000 years. That was redshift up to 1,000, and as time progressed, the universe started to expand, and as it expanded, it cooled down. So it cooled down enough such that neutral atoms started to form around 400,000 years after the Big Bang. And so that's really when we start to see the free streaming cosmic microwave background photons. They're basically free streaming towards us from the surface of last scattering. So we also call it the surface of last scattering, or recombination, and so on. So later, universe evolved further, and it started to form stars and galaxies and all the structures that we know, and now we are roughly 14 billion years after the Big Bang. So we could basically put all these things in those 4 bullet points there. Started with inflation plus hot Big Bang, and then structures grow hierarchically. Gravity is very well explained by general relativity. We are still looking for deviations, but it seems like it's actually pretty good. And then observations tell us that we live in a flat universe. Okay. So one of the strongest evidence for this hot Big Bang is the discovery of the cosmic microwave background. So it is a remnant radiation from the Big Bang. It was predicted in around 1940s and discovered later, 20 years later, at a telescope in New Jersey, accidentally, by Penzias and Wilson. So this radiation is very homogeneous and isotropic, meaning if you look any direction on the sky, they look very similar. They have roughly the same statistical properties everywhere. So there is no directional dependence. And it's almost a black body radiation peaking at around 2.7 Kelvin. So that's pretty much all we need to know about that. The other important fact about cosmic microwave background is that at the time of recombination, when the CMB photons are starting to free stream towards us, there are still some free electrons left, right? Because universe did not go from a dense and a hot ionized medium to suddenly neutral, right? It took some time for it, and at the time there were still free electrons, and CMB photons interact with these free electrons through Thomson scattering, and that gave rise to polarization in the CMB. Okay, so CMB is also partially polarized, and then these CMB photons, when they're traveling towards us from the surface of blast scattering, they are basically interacting with everything that we know in the universe, all the structures, galaxies, everything that we see in the universe. And these interactions, they give rise to this the secondary anisotropies in the CMB. And as you'll see that those are also extremely good astrophysical and cosmological probes. Yeah.
Basic question. We had a talk earlier saying that the CMB was polarized because of gravitational waves. Is this the same polarization that we're seeing, or is this like different contributions to polarization?
Right. So it's different contribution to polarization. So CMB is not polarized because of gravitational waves, but gravitational waves, they just give to a slightly different signature in the polarized CMB. Okay, so we can use cosmic microwave background to study the initial moments of the universe, the contents and evolution, and also structure growth. Okay, so on the bottom we see this really nice image of the cosmic microwave background from 3 different satellites. First was COBE, that was launched in 1990s, and you can see that it has very, very poor resolution, angular resolution, but it's still it was the first one to discover the anisotropies in the CMB. So you can see the dark and the bright spots. Later, 10 years later, WMAP was launched. Very, very good angular resolution compared to COBE, and then later Planck. And you can see we can start to see smaller and smaller structures over time. Okay, Planck has 5 arc-minute resolution or 5 to 7 arc-minute resolution, so it's not great for astronomers, but it's actually great to learn about the universe. Okay, so yeah, so what we normally do as cosmologists, so we take those maps and we compute something called the power spectrum. Okay, so in very simple terms, it's basically if you have an image in Python, for example, you take that image, you make a Fourier transform of the image, and then you basically square it and take the absolute value. Okay, so that's basically the Fourier transform. And then the horizontal axis here is basically the Fourier wave number. In this case, we don't actually do Fourier transform because it's full sky, so we do a spherical harmonic transform. So here it's the angular wave number. So horizontal axis, we call it multiple. So it's kind of important to understand this plot because I'm going to show a lot of these kinds of plots later. So when you're looking at the left side of this plot, we are looking at very, very large angular scales in the sky. When you're looking at the right side of the plot, we are looking at very small angular size scales in the sky. Okay, so it's basically inverse of the Fourier wave number. The vertical axis is the power that we measure as a function of these angular scales. Okay, so you can see there are different curves there showing the power spectrum of the CMB. In red, it's temperature power spectrum. In blue, it's one of the polarization power spectrum. It's called the E mode power spectrum. And then in green, we have the B mode power spectrum. So B mode power spectrum, so that's basically coming from gravitational waves. So basically, when we make this power spectrum, we can actually learn a lot about the universe. So for example, if you look at the red one, if you look at the first peak, we can say, if the universe is flat or curved, we can understand how the matter density in the universe. And if you go into small scales, we can understand how many light relics are in the universe. Similarly, if you look at the blue curve, we can learn how reionization happened in the universe. And then if you look at the green curve, we can learn about inflation itself. Okay, so different parts of this curve serve for different purposes. So it's very important to understand all of these features. Okay.
Question.
Yeah.
Can you explain why the B modes have any information about neutrino masses?
Right. So that portion that you're actually looking,
Yeah.
so that's actually coming from lensing B modes.
Okay,
So that's structure formation.
okay, gotcha.
So
And
if
it's
you,
on small scales because that's where the neutrino mass makes any
Right.
impact on structures?
Yeah.
Okay,
yeah, so that's basically coming from E to B.
okay,
So when you're looking at that, we will learn a sense of form.
I see.
Okay. So this is what we do. So we observe these maps. We take the Fourier transform, and then we combine with external data sets, and we constrain cosmological models. Okay, so this is basically what a CMB cosmologist is pretty much doing in the lab. Okay, so that's all about the primary CMBs. Okay, I will tell a little bit about the blue curve later, but I'm not going to go into any more details about the primaries. Okay. So now moving on to the secondaries, which are even more fascinating, at least for me. So there are like so many different kinds of the secondaries, and these are mostly coming from interaction of CMB photons with the structures in the area. Okay. Just listed some of them here. So one is gravitational lensing. So obviously we have measured gravitational lensing, we have measured CMB lensing. So this is just a remapping of CMB photons based on the deflection angle. So you have some mass, CMB photons are traveling towards us, so they're gonna change their path. Okay, so it's simply just remapping of those based on the deflection angle. And deflection angle is proportional to the lens or to the mass of the halo that's actually lensing the CMB. Okay, so this can be due to large scale structures. So basically, structures in the universe can be due to single halo, clusters or galaxies, and it can also be due to underdense regions like cosmic ones. So next is the thermal Sunyaev-Zeldovich effect. I will explain that in a little more detail later. But thermal SZ is so we call it SZ effect, named after Sunyaev and Zeldovich, two scientists who proposed that effect. So it's nothing but it's simply the inverse Compton scattering of CMB photons. So CMB photons are traveling towards us. Then we have structures. So we have clusters of galaxies. Clusters of galaxies are normally hot compared to the average universe. So they have free electrons. So when CMB photons are interacting with free electrons, they gain extra energy. So that's the inverse Compton scattering. And it's actually a very useful effect. This is how we detect galaxy clusters in CMB surveys. I'll show these later. So next is the kinematic SZ. Very similar to thermal SZ, but this kinematic SZ is erasing because these free electrons are not just static, they're actually moving. Okay, so if they're moving along the line of sight. So if they're moving towards us, they give rise to a Doppler blue shift. But if they're moving away from us, they give rise to a Doppler red shift. Okay, so yes, so it's just a Doppler shift induced on CMB photons due to free electrons. Okay, so they can be due to basically radial motion of halos in the universe. It can be due to the fact that at the time of reionization, these ionized bubbles are moving. They can also be due to the fact that some halos are rotating. So then we have other smaller effect. So one is called the Birkinshaw goal or moving lens. So in the case of KSE, the halo is actually moving along the line of sight, but the halo can actually move in the transverse direction as well. So when the halo is moving along the transverse direction, so this halo is a lens, so it has some gravitational potential, and when they're moving in this direction, so we're basically seeing a time derivative of the gravitational potential. So that gives rise to a dipole in our CMB maps. It's a very small effect. So that is called the moving lens. It has not been observed yet. And then we have integrated Satchel effect or Rishama, the second order Rishama. So these are basically because CMB photons, when they enter a gravitational potential, at the time when the universe is accelerating due to dark energy, these gravitational potentials are growing. So CMB photons enters with some energy, but it comes out with a lesser energy. Okay, so that is this additional effect. So that happens on very large scales. So these are some of the secondaries. There are also like polarized versions of these things. But I'm not going to go into details about those things. Yeah.
Just to check, what you mean by secondary here is you mean anisotropies that happen between like the surface of last scattering and now.
Exactly.
Oh.
Yeah. Okay. So most of these secondaries are on small scales. So we need very nice telescopes to measure these things. And here is kind of an animation showing that we have really good data now. So this is a map of our universe. This is actual data. from WMAP. So it's yeah, as you can see, it's 30 square degrees. So if you look at the same region with Planck, you can see that the resolution has improved significantly. Okay, so you can now start to see more structures. But if you look at the same region with SPD, which is what I and many people in this room worked on, you can see that it's even better. Okay, so the resolution is great. So now, rather than those really big negative and positive blobs, we also see these really small bright and dark dots. Okay, I'll tell you what those are. So if you're used to seeing these kinds of images, you will immediately say that those big blobs are CMB, the primary CMB anisotropies. If you're not, yeah, so these are primary CMB anisotropies. Okay. But there are also these bright spots. So these are actually galaxies. Okay, so when we are looking at the region of the sky using this 150 gigahertz or sub-millimeter telescopes, we don't just observe the CMB, but we also observe things, like galaxies like quasars and dusty star-forming galaxies. They also emit in the same wavelengths. So they appear as these bright spots for us. Okay, so these are contaminations for us. So we tried really hard to get rid of these things, but these are also targets for many people, including a lot of people working on SPD here. We create like point source catalog. Well, I don't. Mel, for example, creates point source catalog for us, SPD. So the bright sources are galaxies, and then we also see these these dark spots. So these are actually clusters of galaxies. Okay, so these really small dots are actually groups of galaxies. And that's actually the thermal SZ effect that I was telling before, but I will explain that in a little bit more detail later. Okay, so this is actually how we detect galaxy clusters in the CMB surveys. Okay, so yeah, so when you're looking at these maps, we don't just see the CMB, but we also see all of these other emissions. And then, so if you compute the power spectrum of these maps, so this is power spectrum from SPD. So SPD observes in 3 bands: 90 gigahertz, 150 gigahertz, and 220 gigahertz. So on the top panel, showing the auto power spectrum of those maps, and on the bottom panel, I'm showing the cross power spectrum between these different bands. Okay, so if you're just looking at primary CMB, so that's just this red line, but you can see that our data is not following this red line when we go into smaller scales. Okay, this is because we're actually seeing emissions from these other things like galaxies and galaxy clusters. So our data basically is composed not just of CMB, but CMB plus all these other things. Okay, so these are crucial for us to understand our data sets. So if we make a mistake in understanding these things, then our inference is going to be very wrong. Okay.
The red line is the primaries alone, the prediction from the primaries alone.
Yeah. Okay. Okay. Right. I think those are lens CMB. Yeah. Okay. All right. So with that, I'm going to get into the KSZ. Because this has been my interest for like more than a year now. Okay, so what is KSZ and why is this useful? So KSZ, like I said before, so this is coming from the fact that CMB photons are scattering of free electrons, but these free electrons are also moving. Okay, so it's Doppler boosting of CMB photons due to free electrons in motion. And as you can see from the equation there, so it is proportional to 2 things. One is the tau is the optical depth, so it's the electron density, and then the peculiar velocity of electrons. So if the electrons are not moving, there is no KSZ, and if there is no free electron density, there is also no KSZ. Okay. So this can be due to 2 things. So we have the CMB here, and we are looking from the right side. So at very high redshift universe, when stars started to form. So I said before that universe was very hot and opaque initially, and then it became neutral around recombination. But then later, as stars formed, universe started to ionize again. So we call it the period of reionization. Okay. So at the time of reionization, we have free electrons again. So that gave rise to this KSZ signals. And then later in the local universe, or when I say local universe, it's basically going from redshift 0 to redshift 3 or 4. Okay. So we have halos moving along the line of sight, so that also gives rise to this KSZ signal. Okay. So these KZ signals, they look very similar to us when we take the power spectrum, which I'll show in a few slides. So one way of detecting the local KZ, since this is coming from halos, galaxies moving, we can actually take our CMB maps and cross-correlate it with galaxy surveys, and we can detect that signal. Okay, it's a very, very interesting signal. We can learn a lot about astrophysics and structure formation, but I'm going to focus on the high redshift signal. Okay, so high redshift meaning redshift around 6 or above. Okay, so that is the signal from reionization, and I'll tell you how to measure that using CMB surveys. Okay, so how do we probe reionization using CMB surveys? So one obvious signal is looking at the polarization power spectrum. Okay, so the reason for this is so at the time of reionization, when there are free electrons, these free electrons, they interacted with CMB photons, and they gave rise to an additional polarization signal. Okay, so we see these bumps here. So that's the polarization power spectrum. So that corresponds to the size of the universe. This peak here that corresponds to the size of the universe at the time of recombination. Okay, but later at the time of reionization, universe was much bigger. Okay, so as a result, when we have a signal at the time of reionization, we expect that to fall at very, very low level. Okay, so this is very, very large scales on the sky. So you can see that when I'm changing the optical depth of reionization, this bump is changing. Okay, so basically, if we observe this bump, we can infer something about reionization. Okay, but it is hard. The reason it's hard is because these are very, very large angular scales in the sky, and we cannot observe those very large angular scales from ground-based telescopes. Okay, so we actually need satellites. So this, for example, the best constraint right now comes from Planck, and we cannot beat it. So we are waiting for. So one is, for example, like Taurus, which Jeff is working on. So Taurus is a balloon experiment, so that will also place really nice constraints on that. Otherwise, we have to wait for Lightbird, which is the next generation CMB satellite. Okay, so basically you can see that this bump that happens at the time of reionization. So knowing where the bump, knowing the location of the bump, will tell us about the size of the universe at the time of reionization, and that translates to a redshift of reionization. Okay, so that's how we probe reionization using this E-mode polarization. Okay, so peak location that corresponds to redshift of reionization, amplitude corresponds to the history. Okay, and then the width also slightly corresponds to the duration of reionization, but it's kind of hard to measure it. So we don't have to just look at the E-mode polarization. We can also look into cross correlation between temperature and E-mode and also B-mode. But those are going to be fainter than this. So I'm not going into detail about those things. So that's one way to measure reionization using CMB surveys. The second way is just looking at the power spectrum. So you can see now it's basically the same figure, but looking at slightly different scales. So that's the temperature power spectrum, and that's the E-mode power spectrum for different values of tau. You can actually see for blue, the power is higher, whereas for red, the power is lower. And that's because when photons are traveling through this cloud, they're going to be attenuated by like either the -2 tau factor. So if we measure that attenuation, we can constrain tau. But unfortunately, this is fully degenerate with, for example, the amplitude of the power spectrum. Okay, so you can see that if we just shift the normalization of this curve, that's also going to move this red into blue or blue into red. So they are both very degenerate.
Is it totally scale invariant? The suppression factor is like truly totally scale invariant?
It is totally scale invariant. But I mean, so this is unlensed CMB, but if you look at lensed CMB, you can break the degeneracy a little. Okay, so that's the second way. And the third way, which is what I'm doing, is to measure the KSZ signal. Okay, so one is a large fainter signals, but I'm not going to deal about those things. Okay, so how do we measure this with KSZ? So this is the power spectrum of KSZ coming from a simulation. So you can see that there are 3 panels here, and these 3 panels have slightly different process of reionization. So in this panel, we can actually see more smaller scale structures compared to the one on the right. And that basically changes the power spectrum. Okay, so you can see that this one has more small scale power, well, it also has more large scale power. But you can see that depending on how the reionization happened, these curves are slightly different. But this is a really faint signal, even though we see a big difference between these three things here. When I plot them with all the other components, it's very faint to measure. Like, for example, this one, okay? So you can see the vertical axis here goes from basically 1 to not even 2, maybe a little bit about 2, okay? But if you look at the same figure with all the other components included, we're just looking at this region, okay? But when we have, when we basically include all the other components, you can see that there are these other colored lines that are more than an order of magnitude higher than KSE. However, yeah.
Can you explain a bit what radio boson is? Is that just
Right.
radio galaxies?
These are just radio galaxies. Yeah. Yeah. So radio Poisson is just radio galaxies. DSFG is dusty star forming galaxies. And then we also have TSE and yeah, and then KSE. So nevertheless, SPD made the first detection of this KSE power spectrum. Okay. So it is a 3 sigma detection that was out a couple of years before. So yeah, so there was the first detection, but one has to be very careful about these measurements because when we try to infer this particular line, we also have to assume a lot about all these other lines. So if our assumption about those things are slightly off, then this is going to be wrong. Okay, so we have to be a little careful about how we want to interpret that. Anyway, it was a 3 sigma detection. So what can we do with 3 sigma detection? I mean, 3 sigma is just consistent with everything. So when we try to constrain reionization with this, we cannot do very well. So this is a plot from TIMS, and you can see that this is our measurement from SPD, and you can see it's basically consistent with so many lines here. So it's not really constraining things much. Okay. So that's where we are now. Yeah.
Why is there only one measurement that are given up?
Right. So this was done because the way this analysis was done was, so we used templates for all these other signals, and then we just tweak the amplitude of the template at L of 3000. So that's why there was just one data point, right? But yeah, so that's another interesting point, because if we speak to the community, they don't want a single data point, they actually want the entire band power. So because you can see from this that the power spectrum changes with multiples. So having entire band powers is really useful.
Is there some part of your analysis though, that if you were to get this for several multipoles, that would make the error bar in each multipole larger? Have you somehow used the information across the spectrum to increase the power at one?
Yeah.
Okay.
So yeah. So that. So because we didn't have a very sensitive data set for KZ, that is all we could do.
Okay.
And it was 3 sigma detection.
Okay.
But I'll show that one of the current analysis that I'm doing, we are improving the signal noise significantly. Okay. So yeah, so this is where we are, and why are we there right now? Because it's very hard to detect the KSE power spectrum. The other problem is that, like I said before, there are these 2 sources of KSE, and when we look at the power spectrum of these KSE signals, they look very similar. Okay, so we are not just assuming something about all of those other colored lines, but we are also assuming something about how halos are moving in the local universe and how halos are forming in the local universe. So that's why it's a little challenging. Okay, and I want to just emphasize why these are hard with these following figures. So challenge A is just detecting this is hard, and here's an example for that. So this is again the power spectrum that I've been showing previously, and now this has only the primary CMB signal, and then this has the KSE signal. And it has some lines for instrumental noise that we expect from future CMB surveys, not current surveys, future surveys. Okay. So you can see that when we are looking at very large scales, it is to the left. We cannot really measure this because this primary CMB is fully killing us. It's basically 3 orders of magnitude higher. Okay. Even though we know it, we'll be sensitive to the sample variance of that. So there is no way we can measure this. And when we go to small scales, we have noise. Okay. But you can see that there is a sweet spot here where the signal to noise for KZ is more than 1. Okay, so if our data is just CMB plus noise and KZ, it's great. So this, if we take the cumulative signal to noise of this entire curve, that'll be several. Okay, but unfortunately, it's not this. So we have these other signals. So first is the thermal SZ signal. So these are basically galaxy clusters and hot electrons in galaxies. So they also emit. And now you see that when I add that, they look very similar to KZ. So now we can already see that KZ is no more going to be single to noise greater than 1 on any of these scales. Okay, so that's KZ. So now let's add radio galaxies. So these are just quasars. So that's doing that. And then finally, if we add signal from dusty star-forming galaxies, basically there's no way we can measure KZ or very well. Okay, so basically what this is all saying is that when we look at the maps, so like the map that we looked previously, and we picked we saw CMB and isotropies, we saw those small dots, dusty galaxies and clusters. So there is no way when we look at a map we can say that that's KZ, because KZ is never going to be more than we'll never have a signal to noise greater than 1 in our maps. So there is no way we can ever visually see KZ signal. Okay, when we just look at the maps. However, when we do a proper analysis, when we take this power spectrum and when we compute the cumulative signal to noise, it's actually not bad. Okay, it's going to be several in the upcoming years. So if you're looking at large scales, CMB is much bigger than KZ. So we want to design instruments that are sensitive to small scales. And then when we go to small scales, CAB is much bigger than KZ. So we want to build instruments such that we can mitigate the CAB scale. Okay, so that means we need low noise, high resolution CMB instruments with multiple frequency bands to reduce foreground contamination. Okay, and the reason I say multiple frequency bands is because KZ and CMB are the same in all the frequency bands. So they are that's the black body spectrum. It doesn't change as a function of frequency, but all the other foreground signals, they change as a function of frequency. Okay, so when we have multiple frequency bands, we can get rid of some of those foregrounds. Yeah.
So TFC doesn't change?
It does. Yeah.
It does.
Yeah.
It does change. Okay.
Yeah. Okay. So these are just pictures about from instruments that I'm working and then other instruments that exist right now. So SPD. So that's what I mostly work on. So it operates in 3 bands, and then we have advanced ACT in Chile. So that also operates in 3 bands. Then we have Simon's Observatory, which is the upcoming CMB instrument. I think it operates in 6 bands. And then the next generation CMBS4, which has even more bands. Okay, so CMBS4 is operating both from South Pole and from Chile. Okay, so but we want, yeah. So even for these future surveys, right? So these future surveys are very low noise. They have multiple frequency bands. But even for these future surveys, we have to be very careful in how we handle our data. So if we just take data from all the bands, not just the 3 bands, but from 6 or 7 bands, and if we combine them, we do it in a way such that the signal to noise improves for whatever we want to measure. If we do it that way, we are still going to be affected by foregrounds, and that's what this plot is showing. So this plot is showing the ratio of KZ over the foregrounds. Okay, so meaning if we want our foreground to be under control, we don't want any of these curves to be above 1. Okay, but you can see that most of these curves are above 1, which means that even for these future experiments, if we simply combine data such that the signal to noise improves, we have to do a lot to mitigate these foregrounds. Okay, but yeah, we showed recently in a paper that there is a different way of doing this. Sacrificing some signal to noise. So if we do a slightly different approach, we can get rid of most of these foreground signals. Okay, so this is roughly the same plot, again the ratio plot, and you can see in this plot none of these curves are even reaching 1. Okay, so at most they are reaching 0.4, but these scales are still contaminated with CMB. So if you go into small scales, you can see that foregrounds are more than a factor of 5 lower than KZ. Okay, which means that sacrificing some signal to noise, we can detect this KZ power spectrum relatively well with the upcoming surveys. Okay, so how well? So earlier I showed a 3 sigma detection, which was out 2 years before. But now we are working with SPD3G. So that's the current telescope that that's the current camera that we're working on. And you can see that the signal to noise is actually 20. Okay, so that's a massive improvement. And then I should emphasize that this is not the best that we can do. This is a good signal to noise with very good foreground mitigation. Okay, so if you have better way of mitigating foregrounds, you can improve the signal to noise even better. Okay. But nevertheless, 20 sigma is not bad. It's great, and that can be achieved in the next few years. Okay, so it's
So when you write the 20 sigma, that's so you previously had your residuals were like a fifth of the size
Yeah.
of your signal, right? And they wouldn't be residuals if you could put small error bars on.
Right.
Right. So is it getting just the noise of 20 because you're getting many L bins or
Yes.
something like that? That's,
Yeah. So
So
you can go over this plot.
in some L bin, the sensitivity is 1/5.
Yeah, exactly.
Okay.
Yeah. So yeah, skip this plot, but yeah, that's why the band for errors.
Got it.
Okay. Yeah. So and then you can see for CMB4, which is a futuristic instrument, the signal noise is 80 or 100 or it's just very high. Okay. So yeah, so this is something that I'm currently working on. So you can see here that so this is also from SPD. Okay, so this is under preparation. So what we are doing here is we are combining data from SPD and Herschel. So Herschel is this cosmic infrared background satellite. So when we include Herschel with SPD, we have a very good mitigation of CAB. Okay, so just by including Herschel and going really deep, it seems that we can recover the KSE power spectrum at roughly 8 sigma. Okay, so that's already a big improvement compared to the 3 sigma detection from the previous data set. So this is something that I'm currently working on, and this is under preparation. But you can see from SIMS, we can recover this KSE power spectrum, and the cumulative signal noise of that is around 8. Okay. Okay, so the first challenge was that noise and foregrounds. The second challenge is even if we detect that total KSE power spectrum, so this plot basically shows why it is hard to constrain reionization from KSE power spectrum. So this is again that power spectrum. So the total signal is this red line. Green is the reionization KSE, and then you see that there is this yellow color line, which is coming from halos moving in the local universe, and you can see that these two lines, they roughly have the same shape with slightly different amplitudes, but we don't know what these amplitudes are because we have never measured these things, right? So this is just a simulation, but that's the problem. So they have same shape and roughly same amplitude. So if you want to say something about reionization, you want to get rid of this yellow color line from the red. Okay, so anything that we assume about this is going to affect our constraints on reionization. Okay, so we have to be a little bit careful about that. But if we assume, for example, a 10% prior on the local KSE, we can actually do really well on reionization. Okay, so this plot is showing the constraints that we expect on reionization. The vertical axis is the midpoint, so that's when reionization happened, or that's when 50% of reionization happened. And the horizontal axis is the duration. So it's basically the redshift width. And you can see pretty much all these surveys, they're not very sensitive to the midpoint, but they're actually really sensitive to the duration, okay? Because that's how KSE works. And then this prior comes from Planck. So this is coming from that large scale bump, E-mode bump that I mentioned before. But if we remove that Planck prior, and if we assume a light board prior, which is futuristic, you can see that these constraints improve by roughly a factor of 3. Okay, so this is looking really nice. But then I just want to highlight this point that nevertheless, I've assumed some prior on the local KSE, so can we actually do better? And it seems that we can do better. Okay, so now moving from power spectrum, we can go to higher order things. So we can look at the tri-spectrum or the 4-point function. So power spectrum is just a 2-point correlation function in real space. Tri-spectrum is a 4-point correlation function. Okay, so there is no 3-point for KSE. There is no 1-point for KSE because KSE. So when you just sum all the pixels, it becomes 0 because in some regions they're moving towards us, and in some regions they're moving away from us. So when you just average everything, it basically cancels. Okay, So only the even orders exist. So that's the 4 points. So this is something we started working on recently. So a paper came out in 2016 by Kendrick Smith and Simone Ferraro. So where they came up with this method where they said, instead of looking at the power spectrum, where these two signals look very similar, if you look at these higher order functions, these signals, they look very different. Okay, so that's what's shown there. So that plot is showing the derivative of the KZ 4 point as a function of redshift. And you can see that that is a bimodal, that is a bimodality there. Okay. So there is a peak at redshift 8. So that's when first stars formed. And then there is a peak at low redshift. That's because the halos are moving. Okay. And you can also see that the amplitude of the high redshift signal is much higher than the amplitude of the low redshift signal. Okay. So basically what this is saying is that when we're looking at the power spectrum, we are simply taking the Gaussianity here, right? So, but when we're going for the higher order functions, we are looking at the non-Gaussian nature of these signals. Okay. And as it happens, the high redshift signal is much more non-Gaussian compared to the low redshift signal. And that's why there is a bigger peak there. Okay. Yeah.
What's capital L? Is that just the multipole at which you're?
That's a recovered L. Yeah.
Okay.
It's a reconstructed yeah.
Gotcha. Can you do any like KSC, something else by spectra?
Yeah.
Okay.
Yeah. Yeah, but for reionization though, we need like a very, very high redshift probe.
Okay,
Right.
that makes sense.
Yeah.
Okay, so you can't use any galaxies or
Yeah.
anything. Okay.
Yeah.
Why is it more Gaussian at low redshift than high redshift? Because that-
Yeah,
that
so-
just breaks my intuition of
Right.
these
So
things are more Gaussian.
yeah, so it's basically the line of sight distance, right? So the high redshift signal, it's basically from redshift 10 to maybe 6. Okay. So if you compute the line of sight distance in that particular redshift window, it's much smaller than if you compute the line of sight distance from us to redshift 3. So basically, even though they start as Gaussian, they start as non-Gaussian, they become roughly Gaussian because of the integration
There's
over
more
the entire line.
bouncing over more.
Right. Okay, so yeah, so they showed that we could actually do really well if we included that higher order function. And then we did some forecast for SPD, and then this is what we found. So this is again the same constraints on reionization. Vertical axis is the optical depth, horizontal axis is the duration. And you can see from 2 point, we are, it doesn't constrain optical depth. And then when we go to 4 point, this degeneracy direction is slightly different. So when we combine these two things with Planck, we get a really nice constraint. So when we include the 4 point function, basically the constraints improve by a factor of 3. Okay, so that's what we found in these forecasts. I was planning to do this, and I said, okay, maybe I should do this at some point. And then Gail basically told me, no, we should definitely look into this. And then we started looking into this in the last 3 months, and it seems actually pretty promising right now. Yeah.
You assume a Planck prior on tau?
I assume the Planck prior on the top, yeah.
So in the next, could we, like, how much better does this get if you have a Lightbird prior on tau?
Right, so Lightbird prior on tau will be a factor of 3 better.
Yeah, so is that maybe, that seems reasonable by the time you're actually detecting?
Well, not for SPD3G though.
Okay.
SPD3G is right now.
Okay, gotcha.
Yeah.
But I thought you said you're not ever gonna detect KSC right now.
Well, we can still set constraints.
Okay, gotcha.
Yeah, so
some of us don't know what Lightbird is.
yeah, so Lightbird is the next generation CMB satellite. So it's Japan and USA mission. And it's currently under I think design stages. I think it's going to be launched next decade. Is that correct?
That's about right. There were times when the launch date was supposed to be very, very soon. I think the US is, I think Quasi dropped out of it. But Europe's involved.
But that's also Taurus, which Jeff is working on.
And class.
And class, yeah.
The ground-based.
Ground-based, yeah. Okay, yeah, so getting back, so Gil said this will be really nice to see the signals, and then we started looking at this, and this is what we find. Okay, so this is simulation. Okay, so this is a map of so what you're seeing here is not KZ. Okay, so we are being dominated by noise here, but nevertheless, it seems that our data and sims look pretty close to each other. Okay, so this is what we get from sims. Okay, when we try to see what we are going to get. And this is what we get from data, okay? So obviously they're not going to be the same because it's the simulation and data, but you can see statistically, they look very similar, right? So the color scales are the same, and you can see the number of blue or you know, the yellow colors or the orange, they look very, very similar between the two, okay? Just saying that, oh, we actually understand our data really well, given in this 4-point space. And then this is a 4-point power spectrum. So this is a 4-point function. So this is a trispectrum. So again, red is simulation, black is data. Again, you can see that they're actually very close to each other, meaning that whatever we think is happening in our sims is actually it's happening in data. Okay. So do we actually know where the KZ is? We don't know yet because we haven't looked at that particular final signal yet. Just because we are doing like other tests to make sure we understand everything. So this line is not the final signal. So it receives contribution from CMB lensing and then other foregrounds. Okay. When we get rid of all of those things, I'm guessing KZ is going to be somewhere here in this at this level. Okay. So signal is there, but KZ is going to be like lower there. And then what can we do with that? So we can now set constraints on reionization. So this, for example, is a plot showing the expected power, assuming some reionization model. So this is the 4-point function as a function of duration and as a function of midpoint of reionization. So I'm guessing that we're going to lie somewhere, we're going to end up somewhere here. Okay, so that's my guess, but we don't have that answer yet. It should be out soon. But we don't need to explore this entire space because we already have constraints from Planck. Okay, so if we take Planck's constraint, so that basically excludes that top region. Okay, so now you can see when we include Planck data, we're going to get better results. Okay, we can also take previous SPD measurement from the KZ power spectrum, and we can also exclude that region. Okay, but we have to be a little careful about how we want to use this measurement. So we want this measurement to be just the 4-point plus Planck, but we'll see where we are. But yeah, basically, I think we can exclude a lot of these regions, and we are going to lie somewhere there. Okay, so that's our expectation, but we don't know the answer yet. Should be out soon. Okay. All right. So I guess that's all about KZ. I want to show a few more slides about thermal SZ. Are there any questions about KZ? Okay. Yeah, sure. Okay. So thermal SZ. Yeah, this is going to be pretty short. So like I said, thermal SZ is the inverse component scattering of CMB photons by free electrons, and these free electrons are inside our clusters. Okay. So this is a very useful signal for us because this is how we detect clusters in our CMB surveys. I showed a map earlier. So this is actually this is another platform data. So that's a map from SPD poll, a previous generation SPD survey. When we zoom into that map, we see these bright spots and dark spots. So those dark spots are actually clusters. Okay. So one nice thing about thermal SZ and why it is important is that this signal is independent of redshift. Meaning, if you want to detect clusters at redshift 2 or 3, this is the only way that we can detect them. Because when we're looking at optical surveys or X-ray surveys, flux obviously drops as a function of redshift. But since SZ signal is independent of redshift, we can actually measure very, very distant clusters from CMB surveys. And then this is a plot showing that this thermal SZ signal is actually dependent on frequency. So this is an image detected of a cluster detected by Planck. So if you look at that region in different wavelengths or different frequencies, you can see that the signal is changing. Okay. So we don't look at these very low frequencies. So we look at somewhere close to here, and there, and you can see that at 217 there is actually no signal. Okay. So basically, what's happening is that the CMB photons are basically moving to higher energy. And so we get a decrement here and we get an increment on higher frequency bands. So what can we do with this signal? So we can build a cluster catalog. So when I say build a cluster catalog, we know the position. So we have the array and text of these things. And then so what can we do with that? Okay. So why are galaxy clusters interesting? So this is a very, very quick schematic to show that clusters are very good probes of structure formation, in this case, dark energy. So there are two panels. These are coming in from simulations. And these two simulations are different in that one does not have dark energy in it. Okay, so we are seeing the cosmic web there. And then the yellow circles are galaxy clusters. So you can see that these are sitting at the nodes of these filaments. So statistically, the top panel and the bottom panel, they look very similar. Okay, so there are equal number of galaxy clusters in the top panel compared to the bottom panel. And this is at redshift 0. So if you're looking at cluster catalog at like in the local universe, we cannot say much about dark energy. But if you go to higher redshifts, you can see that we can see that these two sims are very different. So in the top panel, we have less yellow dots. The bottom panel, we have more yellow dots. And if you go to even higher redshift 1.4, you see there is only one yellow dot in the top panel, like more in the bottom panel. The reason for this is that assuming that there are same number of galaxy clusters in both the panels, in an universe without dark energy, these clusters can form really rapidly because there is no accelerated expansion. So structures form much more rapidly. So all of those clusters are forming very, very rapidly at late universe. Whereas in a universe with dark energy, you need more time for these things to form. So it takes a lot of time for these clusters to form. So the bottom line is that if you measure higher and higher redshift clusters, you can place really nice constraints on dark energy. Okay. So, but to do that, we need to know the redshift and we need to know the mass of these clusters. So unfortunately, this SZ signal, I said it's really good to detect these high redshift clusters. Since they have no redshift information, we only have the candidates, we don't have the redshifts. Okay, so what we want to do is we want to follow with other surveys to get the redshift. We can use lensing to measure their masses, and then we can do cosmology with these. Just maybe 3 more slides. So this is basically the detection sensitivity for clusters from future survey. Okay, so horizontal axis here is the redshift. Vertical axis is the mass, the minimum mass that can be detected as a function of redshift. And these dots are all the ones that we have already detected. And then these colored lines are basically the ones that we expect from future surveys like CMB S4. So you can see actually in the next plot, we can see that so this is pretty much the same thing, but showing the expected number of clusters as a function of redshift. So vertical axis is the number density, horizontal axis is the redshift. These are the ones that we have already detected, and those lines are the ones that we expect from the future survey. So you can see at redshift 2, we can expect actually like 2,000 clusters if they're there. Okay, so this is going to be revolutionary for high redshift cosmology. So on low redshift, pretty much LSST is going to capture everything, right? So we cannot beat LSST at low redshift, but high redshift is a unique discovery space for CMB surveys. So we take these clusters, and if we do some forecast for say dark energy or neutrino mass, we actually get really nice constraints. So basically, what this plot is showing is that the constraints on dark energy equation of state can be sub-percent level, and the constraints on neutrino mass is roughly 28 MeV. So that's going to lead to something like 3 sigma detection of the sum of neutrino masses. Okay. So it looks great. I think I'll probably skip the white stuff. Then I'll go to the summary. So summary is that current and future high resolution CMB surveys are excellent for studying the secondary CMB anisotropies. So explained about KSZ and PSZ. So KSZ is looking really promising, and it seems that with SPD we will set probably the first constraints on reionization using the non-Gaussianity of the KSZ. And then in the future, it looks very promising. 80 sigma or 30 sigma detection from CMB-S4 or SPD, which will give a very nice constraints on reionization physics. And thermal SZ, with SPD and with CMB-S4, we can detect a lot of high redshift clusters. And using that, we can constrain both astrophysics and cosmology. For example, some of neutrino masses could be a 2.5 to 3 sigma detection, and then the sigma W can be roughly 1% or some percent low. And yeah, I'll stop there and take more questions. Thanks, everyone.
Thanks very much, Srini. So time for a few questions.
Is, you talked about how the TFC kind of and KFC have similar shapes, at least at the power spectrum level,
Yeah.
right? Is there any way you, yeah, I'm just curious if there's some way you could like use, because the thermal KFC really is coming from like thermal electrons in galaxy clusters, right? Is there any way you could cross this with a map of clusters and at low redshift and subtract out TFC?
Right, yeah, we can do, well, I mean, one easy thing to do would be to just mask out all of the detected clusters.
Uh-huh,
So just doing that gets rid of most of the things.
uh-huh.
But we can do additional things like, crossing,
Okay,
getting some external information for TAC.
okay, gotcha. And where's the, yeah, so like, you mentioned a TFC prior, but it might be reasonable. What sort of?
So that prior comes from bispectrum.
Okay,
Yeah.
gotcha.
So you talked about the 4-point correlation function and how much additional diagnostic power it offers.
Yeah.
But are there certain requirements of the data, like in terms of the field of view of your survey or the purity of your survey that are imposed by trying to measure the 4-point correlation function?
Right, yeah, so when we go to like higher and higher order functions, yeah, we want to make sure that our noise levels are lower. So that's one thing. Yeah, so the field of view is also important. So right now we are doing it with a very, very small patch. We are doing it with only 100 square degrees. But if we did it with a full SPD survey, which is 1500 square degrees, the constraints are going to improve by square root of 15. Yeah, but it seems that, I mean, SPD is really good for doing this. So it seems that we can already do this up to some extent. But yeah, in the future, all of those things should be taken into account. Yeah.
We have a question, Brian, floor is yours.
All right. So thanks for your talk. So I just had a basic question about the kinetic SZ. So for the thermal SZ, as you were just saying, the signal's mostly from galaxy clusters where there are a lot of electrons and they're really hot. For the kinetic SZ, and forgive me, you may have already explained this, but where does most of the signal come from? So it's electrons undergoing bulk motion. So what sort of systems are the dominant source of the signal?
Right, so in low redshift, these are mostly like low mass halos. Yeah, something like group scale. And at high redshift, these are just these really big ionizing clouds moving with some bulk velocity flow in the universe. Yeah.
Got it. Okay, thanks.
If I could just follow up on that a little bit. Why does the reionization bubble actually require the electrons to be in motion?
Oh, because they're just moving with the velocity flow of the universe at that redshift. Right, but if they are just stationary, there is no KSE.
Right, but what generates that bulk motion? Is it the reionization process itself, or just peculiar motions?
Just peculiar motions. Yeah, reionization itself does not do that. Yeah.
What's what kind of motion? A peculiar motion?
Peculiar motion.
What is that?
Oh, peculiar motion is just motion with respect to the frame of reference. I mean, the universe is moving I mean, that is this accelerator. Well, that is a frame of reference for the universe, but then these halos are moving, with respect to that frame of reference. So that's
They're pulling on each other.
Yeah.
Okay.
Any other questions?
Thanks, everyone.
Okay, it's nice to meet you again.
I do have a question, but I don't want you to be on the recording. All right, so I had two